So today what we'll do is we'll review the homework assignments from last week and answer any questions that you guys have. As you know, feel free to post them during the week if you are able to get a chance to work on the homework as problems. You can always post those to the website and we can answer them before the lab session. But we'll go ahead and get started. So if you have, while I'm pulling up the files and getting my system going, if you have any questions that you'd like me to address during today's lab session, feel free to type them into the questions box. Okay, well, I don't see any questions at the moment, so we'll go ahead and start by just reviewing the questions that we had that we were going to work with. Really, there were two problems. The first was working with the data from the atorvastatin studies, and we were specifically for the homework looking at the data comparing 80 milligram atorvastatin and placebo. And there was some sample R code for the data manipulation components that we covered in the lecture last week. And as we noted, the endpoints that we're going to be working with are LDL, PCFB for percent change from baseline, and the corresponding standard error. So the problems asked us to really after reading in the data, to simply start by plotting the data using the forest plot. And I wanted you to look at a few different ways of trying to make those plots look nice or look the way that you'd like them to look. There's lots of different options as we talked about last time, and I was just hoping you could get a chance to explore some of those. And then using that plot to try to understand whether you felt there was any between study variability in that difference from placebo. Given that that after making that plot, then the idea was to fit a fixed effects model, look at the weights that are coming out of that model, and try to ascertain whether there's any study that's having a particular influence in the results. Extract the estimate of Cochrane's Q statistic, and then make some inference or decision about what you'd conclude about statistical heterogeneity in the between trial difference and the difference from placebo. And then following on to that, fit a mixed effects models, a couple different mixed effects models, compare and contrast between methods for estimating tau squared, and then look at I squared and make some inference there. And if you had time, to fit a Bayesian model. I'm not going to focus too much on the specifics of using the forest function, but I will highlight a few points as we're going through these questions today. What I would like to spend a little bit of extra time on is the modeling in BUGS. But as I said, if you have any questions along the way, please pop them into the questions window. So without any further ado, we can get into looking at the script. I hope this is large enough for you all to see, but and if it's not, please let me know. So we'll start by loading our libraries that we'll use in the session today. First is the metaphor library that we've seen before. The second is the R to WinBUGS library, which we will use to call WinBUGS from R and to post-process the output from WinBUGS. And the last is the EMD book library, and we'll use one particular function from that library to convert output from WinBUGS into a CODA format that's easier for plotting in some cases. So next I'll load my, or set my working directory. And I see I have to make one quick change here. So we'll set the working directory, and then we'll read in the data and create the difference from placebo. This is all code that we looked at last week in our during the lecture section. I see here I have a typo in the solutions here. The question asks you specifically to work with 80 milligrams of atorvastatin, and so we want to make sure that we're selecting the right doses of atorvastatin. To the key change here being changing this from 10 to 80. And then to make a forest plot, we'll sort the data, and again, this is all code that we saw last week. Oops. No package called metaphor, all right? So let me point specifically to the library here. Not sure why those didn't load. They ran before. All right, well, let's point to this library. We have our library in, let's come out here to our, oh, I know what happened. So you should have these libraries installed in your MI260 class folder, which for me is here. And then in program files are R215.2 and then library here. So let's copy this. And we'll tell it here our library location is here. Oops, gotta put in the right library again for the EMD book. Okay. All right, so we should now be able to make our plots here, our forest plot. Huh. Which version? I see. I think I kicked off my R session with the wrong version of R. Let me restart this. Going back here, just kicking off R using our version of R from here. There we go. That should solve all of my problems. Okay, there we go. All right, so now we've got our libraries loaded. We've set the working directory to the location of where the data is going to be. And then I'll read in the data. To remember to make this change here to set that to the 80 milligram dose group. And then we'll make our plot with the forest plot. So you can see for this particular dose group, instead of having 8 studies like we had before, we now only have 6 studies. And the average effect, as you might expect with 80 milligram atorvastatin, is larger than we were looking at during the lecture when we were looking at the 10 milligram dose group. So we're going to work with these 6 studies and see what we can come up with for our analysis. So what would you conclude in terms of between study heterogeneity? It does look like there may be some evidence of heterogeneity, as we can see the smaller studies here with the smaller squares tend to have a wider variation in terms of the mean effects, whereas the 2 big studies are tending to fall more in the center of our distribution. In terms of fitting a fixed effects model, again, we went through this during the last class. We use the RMA function with our method equals FE. And to run that, if we were to print that object, we see here that we have a Q statistic of 17.3 on 5 degrees of freedom, which is a statistically significant value of Q, which would indicate that there is statistically significant heterogeneity. The overall estimate is about 56.7 point difference from placebo, with a confidence interval that goes from 59.4 to 54.0. If we were to, one of the elements of this question was to demonstrate, or for you to try to figure out how to extract the weights from a fitted object from RMA. There is actually a weights function that we can use to extract those. And so if we're interested in seeing what the actual weights that went into the analysis are, it would be simply a call to the weights function. If we wanted to look at the relative weights, we can simply take the output from the weights function and divide by the sum of the weights. And that would show us here that we have the study P00692 is getting approximately 24% of the weight. 981-25 is getting about 27% of the weight. Much more even distribution of the weights than we saw with the 10 milligram dose. And again, if we, as we saw, we could simply look at the output here to identify the Q statistic and corresponding p-value. And if we wanted to extract those, we can extract them directly from the object itself by noticing that we have the QE element and the QEP, which correspond to the Q statistics for that model. Why don't I stop there and see if there are any questions quickly? Okay, for the sake of time, I'll just keep moving through. Question 4 asks us to fit two different random effects models using both the Dersimonean and Laird estimator of tau squared and the restricted maximum likelihood estimator of tau squared. So I'll just fit those 2 models here in these 2 lines of code. We can see the only difference between these 2 calls and the previous call was that we're just changing the method for estimating tau squared. In order to see how the estimates compare, we'll look at the tau squared estimates from those 2 models. We see that the Dersimonean and Laird estimator is giving us an estimate of tau squared of about 28, and the restricted maximum likelihood estimator estimates that to be 34. And so the question that I would pose to you is, are those different and both quantitatively or statistically, as well as thinking about what could the impact be in terms of the inference about the overall mean effect. So as you're thinking about that, you may think about, well, it's perhaps more important to consider these on the standard deviation scale. And if we do that, we see that the differences appear to be a little bit smaller. Now we're looking at a 5.3 versus 5.9. And We also would like to think about the fact that these are estimated with some uncertainty, and it would make sense to try to account for that when we're making this simple qualitative comparison. So we can use the conf_int function and apply that to our RMA object. And if we need to, sometimes we'll need to, this uses a simplex algorithm for finding getting the exact confidence limits for tau squared. And so we sometimes need to increase the maximum value of tau squared in that for that algorithm to work. So maybe we can bump this up to 500 and see if that gets us to where we need to be. And it does. And so now we see here from our FIT2, which was the model that used the Dare-Simonian and layered estimator, we get an estimate of tau squared of 28.3 with a confidence interval, 95% confidence interval that goes from 5.2 to 297.5. So quite a bit of imprecision in that estimate of tau squared. And similarly, for the REML estimator, we get a different point estimate, but the same confidence interval, and that's because of the nature of these exact confidence intervals. We're getting the algorithm works out that the confidence intervals are the same. If we think about that on the scale for the standard deviation, it's ranging from about 2.3 to 17.2. So quite a bit of uncertainty in our estimate of the between study variance. And now, the other thing that to keep in mind between the fixed effects analysis and the random effects analysis is the fact that these weights do differ. And we haven't talked about how the point estimates differ, but let's think for a minute about how the weights differ. So I just wanted to insert a little bit of code here to demonstrate how those weights are different. So what I've plotted here, this might be difficult to see on the screen, so I'm going to change this color here from gray to black. I hope that's a little bit easier. What I've plotted here is a dot plot that compares the fixed effects estimate. Oops. I see. There's not 8 studies here. We only have 6 studies. That's the problem. And so let's rerun this. There we go. What I plotted here on the y-axis is the meta-analysis weight. On the x-axis, I've got a group of dots for the fixed effect weights and a group of dots for the random effects weights. And the dots are connected for each of the studies. So this dot corresponds to the fixed effects weight from the study with the smallest amount of weight, and this corresponds to the same fixed effects weight from the study with the largest amount of weight. And if I make one more quick change here, what the red line represents is the average weight if all studies were to get the same amount of weight. So that would be a random effects model where we have quite a bit of between study variability that kind of overwhelms the within study variability. And in that case, all of the studies would get equal weight. And so what we can see is that the random effects model, we can see here clearly how the random effects model is shrinking those weights from the extremes of the fixed effects model towards a model that would be pooling them with equal weights. And you can see that for some of these large studies and small studies, the shrinkage in that weight is rather extreme. And that's partly because of the degree of between study variability relative to the within study variability we have. And if you are comparing fixed and random effects weights, sometimes this sort of plot or evaluating the relative weights from the two models will be a useful thing to consider. So let's go ahead and work with the REML estimator for our random effects model. And that model was FIT3 in my control stream. So we'll look at the values of Q and I squared. And again, we see Q is large, I squared is around 75%. So both giving us a strong indication that there is a significant amount and meaningful amount of heterogeneity. And based on all of those pieces of information, my preference would be to work with the random effects model. And then here's a bit of code simply to add in those the fixed effects and the random effects estimates on top of the data. And we can see the point estimates between the fixed and random effects models don't change very much, but our confidence interval with the random effects model is somewhat wider, as we would expect. So before I jump into the Bayesian model, I just ask if there's any questions. Okay, well, if we don't have anything, I'll go into the Bayesian modeling, where I was asking you to fit a random effects model using WinBUGS, and you could use your choice of prior distributions for the overall mean and for tau squared. And so the way that I'm approaching this, and as we get into using model-based meta-analyses and fitting things in WinBUGS, we're going to code our models as a separate script file. But for these relatively simple models, we'll take advantage of the fact that the R to WinBUGS function allows us to define our BUGS function as our BUGS model as an R function. So I'll define an R function called myModel, and the inside of that function, the internals of that function, are the WinBUGS code to define the model. And so here I'm saying that I'm going to loop over the n studies that I have. Remember, WinBUGS isn't actually processing this as a loop, but it's simply using the loop to define the model. So for here, we'll say that the theta hat I, that's going to be my data, the difference from placebo, follows a normal distribution with a mean of theta I and a precision, or inverse variance, of prec theta hat I. Then we say that the theta hat i's themselves, this is the next level of the hierarchical model, follow a normal distribution with a mean of mean diff. This is the overall mean that we're interested in making inference about. And a precision of, I just label that as prec. This is the inverse of the variance, and that it's really that variance or standard deviation that we're interested in. And then I'm saying that the precision of each of these individual observed data are 1 over the standard error squared. So the pieces of data that I'll be passing in will be the theta hat values, the S values, the standard errors, and the number of studies. Now for my prior distributions, I'm putting a prior distribution on mean diff, and I'm going to say that's centered at 0 with a precision of 10 to the minus 4, or a variance of 10 to the 4. And then I'll put a uniform prior distribution on tau, which for my model is the between study standard deviation. And that uniform prior distribution will go from 0 to 100. And then I just define prec, which is what WinBUGS needs to define the normal distribution, as the 1 over a tau squared, or tau to the power of minus 2. So if we just run that little bit of code, R defines that function. Now I'll define a list here that includes the data that I'll need to pass into WinBUGS. So this is my theta hat is the diff variable that I had in my TOR10 dataset. SE diff will be associated with the S variable in my WinBUGS study, and the number of trials here is equal to the number of studies in the WinBUGS code. So we'll run that just to define the bugs data. We'll define the parameters that I'd like to monitor for my bugs run, and define a function that generates initial values for the Markov chains. And in this case, I'm going to define initial values for the variables mean diff and tau. And I'm going to let WinBUGs itself generate the initial values for the theta variables. I could, because they're random variables, I could also define those in the initial values if I want to. And for these simple models, it's probably adequate to not define initial values for those parameters. But as we get into more complex hierarchical model-based meta-analyses, we're going to find that we'll often want to define initial values for those individual level parameters as well. And then running WinBUGs is simply a call to the bugs function. I pass in the data. I pass in my function for the initial values. I pass in the parameters that I want WinBUGs to monitor. And then I tell it what my model is. Here I'm giving it the name of that function. Behind the scenes, what Bugs is going to do is it's going to write that out to a text file and then use that to be read into WinBUGs. And alternatively, if I had already had that text file, I could just give the name of that text file here. For this particular run, I'll run 3 Markov chains. I'll tell WinBUGs to run 10,000 iterations and use of those 10,000, we'll consider the first 2,000 to be the burn-in. And I won't do any thinning. I'll keep all of the Markov chain samples that or Monte Carlo samples that we're getting from the Markov chains. And then finally, I'll set the debug option to be true, which means that it'll leave WinBUGs open after it finishes. I'm going to do that simply so I can show you some of the plots that it'll make in the log file. Typically, when you're running this in, if you have a model that's running or you're running it in kind of a batch mode, you'd set that debug option to false. So let's run this. What R is going to do is it writes out all those files, it launches WinBUGs for us, and it finishes running our model there pretty quickly. So let's look at what we get. This is a kind of standard WinBUGs output if you're familiar with that. And I guess I am assuming to some extent that we are familiar with WinBUGs. So we get our node statistics here for the nodes that we monitored. The ones that we're going to focus on today are the mean diff and tau. But of course, if we're interested in individual predicted study level mean differences, we could look at our thetas. And then it also gives us our trace plots for the variables. And we can see that they're all mixing nicely, and they look like these nice fuzzy caterpillars that we were taught that to look for in MCMC diagnostics. So now what we get back is an option that I've called REBUGS1. And if we look at that, we have that object has lots of elements. What we're going to focus on is there's an element here called sims.list, which gives us the MCMC output in list format. You can also get that in an array format or in a matrix format if you prefer to work with those. We can do a number of things with this object. If we plot the object, we'll get a plot here that is difficult to see. What it's plotting here is the R hat statistics for each of the nodes that we've monitored, and those in terms of for a convergence diagnostic, we'd like to see those being close to 1. That's from a Gelman-Brooks diagnostic. It gives us 80% credible intervals for each parameter that we've monitored, and it's hard to see here, but also separately for each chain. And then we get a similar kind of plot over here where it's collapsed over all 3 chains. And then if we want to look at that, we can also print the object, and this gives us output that's similar to what WinBUGs itself was giving us, but now this is based at R is doing the calculations. So we can see that our, for example, that the R hat values are all 1 to 1 decimal place. Our posterior median for the mean difference is 56.8, and a posterior median for the between study standard deviation of 7.3, with a 95% credible interval that goes from 1.8 to 21.1. Now, one thing to keep in mind here is that we ran 3 chains. Each chain has 8,000 samples, so we have a total of 24,000 samples. Remember, they're not independent samples in MCMC sampling. So we have to keep in mind that our effective sample size, which is what's shown here, is something typically less than 24,000. So for our mean difference, we have an effective sample size of about 10,000. And for our between study standard deviation, we have an effective sample size of only 1,000. So if you really wanted to get more robust inference, we would want to take longer Markov chain sampling. So perhaps triple or quadruple the number of MCMC runs that we're running. But for this simple little example, I'm going to leave it at 1,000. If we were interested in making nicer or working with the code output, making nicer trace plots, we could use the as MCMC bugs function. This is the function that comes from the EMD book library. And then we could, for example, make plots using the CODA library. So we could get plots that look like this, which is giving us our trace plot as well as a posterior density plot. I won't spend much time looking at those plots, assuming that you've had some background in Bayesian analysis already. And then if finally for this particular problem, if we wanted to overlay the maximum likelihood fit of the random effects model with the Bayesian fit from the random effects model, we can do that with the add poly function, where I'm plugging in here the estimate as the posterior mean value. You could choose posterior median if you prefer. And I'm passing in the variance to be the posterior variance. And we can see here that, again, the point estimates are similar. The central tendencies are similar, but the Bayesian analysis is giving us a wider credible interval. That's in part because the Bayesian model is accounting for the uncertainty in the estimate of the between study variance, whereas the maximum likelihood estimate is not. So I think I'll stop there again and ask if there are any questions. Feel free to type them into the chat box. And if there are, after we address those, we'll move on to the problem number 2. Okay, well, since there are no questions, we'll forge ahead. The second problem, let's pull that up, was related to the 12-month mortality data from the Yip et al. Study that we discussed during the last lecture, where the comparison was to compare gemcitabine plus chemotherapy regimens to gemcitabine alone. As I highlighted, what we are interested in getting an estimate for is the odds ratio comparing gemcitabine plus chemotherapy to gemcitabine alone. And so I gave you the formula and then an approximation to the variance of the log odds ratio, which is an asymptotic approximation. But that's the variance that I was suggesting that you can plug in terms of answering the questions. So the exercises really were to walk through similar sorts of things as we did for the atorvastatin data. Reading the data, plotting the data, assessing visually whether there's between study variability in the odds ratio, fitting a random effects model, combining the data and or the fixed and the random effects estimates, and then doing fitting a Bayesian model. So let's look at those now. And again, all of this code has been posted to the class site. So we'll read in the data, calculating our log odds ratio. Here, using the standard formula for the odds ratio and calculating the asymptotic approximation to the variance of the log odds ratio here. We can make our forest plot with code that looks like this. And one of the exercises, one of the things I was hoping you could explore with this exercise is exploring the options for using the A trans F and the trans F options to the force function. For the data that we're passing in here is the log odds ratio and the variance of the log odds ratio to give us the point estimate and the uncertainty in those, the forest plot points. And if we didn't specify any transformation, what we would get would be a plot on the log odds ratio scale. And it would look something like this. So here we can see on the scale, although I haven't changed my label, this is actually the log odds ratio. If we are interested in plotting that on the log odds ratio, on the odds ratio scale, we really have two options. One is to transform the axes, which is what A trans F will do for us. The other is to transform the data, or the data that's coming in, and that's what the trans F function does for us. So for the first option, the first option that we'll look at is to transform the axes. And that's really just like putting the axes on in this case, the exponential scale. We're back transforming from the log scale to the original scale. So in that case, our transformation of the axis needs to be that exponential function. And so now you can see here the scale here is not linear, but it's exponential, or it's on log scale, I guess you could think about it. Also transforms the descriptions that are plotted on the right-hand side. So we're getting now both the labels and the axes are on the logs, or on the original odds ratio scale. And it sometimes takes a little bit of futzing around with the axes to get the axes to look nice. One nice feature is that there's an A-lim function that allows us really just to focus in on the limits where the data are being plotted and not to have to worry about buffering the X limits to account for the study labels and the numeric labels on the right-hand side. There is an XLim function, an XLim option, and if we were to use that, you can see that, that what we get is a graph that now scales the entire axes to be scaled with the XLim, and so it just doesn't look quite as nice. So if you want to make prettier plots, it's probably safer to work with the A-lim option. So the other alternative is to work with the trans-F option, and if I comment out my options for using A-lim, and I uncomment the options I have here for using trans-F, we'll just show you what that looks like. This gives us a plot now where the data itself and the confidence intervals are transformed using the exponential function, and then they're plotted here on the appropriate scale. And so in this case, with confidence intervals that are spanning, the lowest limit goes down to about 0.08 and the highest upper limit goes to 13. With such a wide scale, the plot of the odds on the odds ratio scale directly with linear odds ratio axes gets very scrunched up. And so that becomes sort of perhaps in this case, a less appealing plot than the one where we transform the axes themselves. So I hope that you were to have an opportunity to explore those options. Fitting the models really is the same as what we've done previously. We'll pass in our log odds ratio. We'll pass in our variance of the log odds ratio. In this case, we'll just directly get both the REML estimator for the random effects model as well as the simple fixed effects model. We'll call those fit.re and fit.fe respectively. And if we were to look at them, fit.re gives us an estimate of tau. The between study standard deviation comes out to something very small, 0.001. And our estimate for I-squared is about 0. There's some numbers out there beyond 2 decimal places that it's not exactly 0, but for all intents and purposes, models telling us that there's really no between study or very, very little between study variability in the odds ratios. So we could then, that might suggest that we could go ahead and use a fixed effects model, and we could certainly do that legitimately, or we could continue to use the random effects model, realizing that what the inference that we'll be making would be nearly identical to a fixed effects estimate, because that estimate of the between study variance is so small. Again, making a forest plot, overlaying the two estimates here. In the force function, I'm taking advantage of the fact that I can pass in the RMA object. Again, I need to tell it if I want to plot on the odds ratio scale, I'll use the A trans F option. And for that A trans F option, where I tell it to put the axis ticks and what the A limits are on the log scale, because everything is being then, after the fact, being transformed to be plotted on the raw scale. I'll put a reference line. I want a reference line at 1 on the odds ratio scale, so that corresponds to 0 on the log odds ratio scale. And lastly, when I add my red polygon here for the fixed effects model, again, I want to pass in the A trans F equals X option. And as we can see graphically here, as we saw numerically, the estimators and the confidence intervals in this case are identical out to 2 decimal places. So before we move to the WinBUGs, I'd like to just check and see if there are any questions. Okay. Seeing that there's no questions, I'll just point out we fit this model. I fit this model today using directly the log odds ratio. I could have put it in as a question for the homework, but I'll just ask you to consider following up on your own if you're interested in considering how you might have fit that model in using the RMA function by plugging in the number of deaths and the number of patients surviving to 12 months in the 2 treatment groups directly, rather than passing in the derived log odds ratio. And the way that you can figure that out is if you look at the help for the forest function. I'm sorry, help for the RMA function. Oops. Help for the RMA function. We can see that one option here is to pass in these 4 variables A, B, C, and D. And if we look at the help for the scalc function, that tells us what those are. It tells us the elements, that these are the elements of the 2x2 table. For the upper left, upper right, lower left, and lower right cells of that 2x2 table. So you'd need to sort of mentally construct what would your 2x2 table look like, and what would be the corresponding A, B, C, and D values to be plugged in there. In addition to that, specifying those, then you'd need to specify a measure here, and for this analysis, the measure could either be the odds ratio, which is the scale in this case that we'd want to work on. We could alternatively, if we're interested in risk ratios, use the relative risk as a measure, or the risk difference. In this case, RMA could do the meta-analysis for you on any of those scales. Okay, so let's move ahead to how we might code this in WinBUGs. And if we're simply plugging in the log odds ratios directly, then our model looks very much identical to what we used before. Again, our theta hats, in this case, instead of being difference from placebo, would be the log odds ratio. The standard errors are going to be the square root of the variance of the log odds ratio. And really, otherwise, we have our model is, the model itself, in fact, is the same. What's only changing is the data that's going in. So we can run that. Here we see this is defining the data, and you can see here that I'm defining in the WinBUGS model, I've got something called theta hat. In the data set, I'm using my log odds ratio. Again, S in the WinBUGS model corresponds to the square root of the variance of the log odds ratio, and the number of studies is the number of rows in my data set, since I have one row per study. The parameters I'm interested in monitoring, again, are the mean difference, tau, and theta. And my initial values, I'll use slightly different initial value mean and standard deviation for this model. In fact, probably using a mean of 0 for sampling of the initial values might make more sense. And then the call to WinBUGS is, in this case, I'm using exactly the same, three Markov chains, 10,000 iterations with a burn-in of 2,000. And it cranks through these samples pretty quickly. So we can see here, in this case, we have, I didn't point it out before, but in this case, we have 15 studies, as opposed to the 5 we had for the previous analysis. Here we see our trace plots for the individual predicted log odds ratios from each of the 15 studies. I'll just scroll through those quickly to get up here to my chains for the mean difference and chains for tau. And now these chains don't look quite as hairy caterpillar-ish as the chains from the atorvastatin analysis did. And that's because there's a higher degree of autocorrelation in the posterior. And we'll see when we get to looking at the output from the BUGS function that that's going to translate into a smaller number of effective sample size. But fortunately for us, the 3 chains here are mixing rather well, so we can see that the green, blue, and red lines are intertwining. And so we can feel confident that that the chains have converged, and we'll feel even more confident once we look at our R-hat statistics. So let's do that now. We'll look at our model output, and we see here that we do have R-hat values of all, at least out to 1 decimal place, equal to 1. But our effective sample sizes, even though we're taking samples of after a burn-in of 2,000, we're taking 8,000 samples from 3 different chains, so that gives us a total of 24,000 MCMC samples. We really only have effective sample sizes here of about 350 for tau and 560 for the mean difference. So clearly for this analysis, that's too small, and we would really need to substantially increase the MCMC runs to get more precise inference from the posterior distribution. But again, for this toy example, I'll just leave it at that, and I'll let you run them longer to see what your final inference might be. If you're interested in making trace plots for some of these, let's just extract the data into a CODA format and then look at the trace plot for the mean difference here. This isn't a very particularly pretty plot, but that's what you get out from the CODA package, that choice of colors. And it's a little bit hard to see. Maybe we'll just look at one of these chains separately, just to emphasize the autocorrelation in the chain. So let's just look at that first chain. You can see here there's quite a bit. The chains are really they're not bouncing around a lot. They're really slowly trending up and down, which tells us that it is mixing and spanning a lot across the space, but because it's taking so long to go from a small value to a big value, we're seeing quite a bit of autocorrelation, which is translating to that small effective sample size. If we wanted to make the forest plot, we could do that in a similar way as we had done previously. And again, we get similar inference as we would get from the classical random effects model with a slightly wider confidence interval. Now what I've done here is I fit a model for us that relies on this asymptotic approximation to the variance of the log odds ratio. We could fit this model alternatively in WinBUGS using the binomial distribution. And I will, for the sake of completeness, post a model, a small chunk of our code that will fit that particular model and allow you to make comparisons between the two different inferential approaches. One of the benefits of fitting the model in that context is that we're not making this approximation to the sampling variance of the log odds ratio. Fortunately, well, some of these studies are rather large studies. Some of them are not particularly large. If we look at our data set, some of these studies, for example, have about 50 patients in them or less. So that might call into question the reliability of that asymptotic approximation to the variance of the log odds ratio. And so a model that models things on the binomial scale that doesn't rely on that approximation might be more robust. So I will I'll post that to the website later this afternoon. So that's really bringing us close to the close of our lab session for the day. This is scheduled as a 1-hour lab session. So I would I'll again open it up for any questions that anyone has, either on the Bayesian modeling or on the use of the forest or the RMA functions. Okay, well, it looks like there aren't any questions. As I said at the beginning, please feel free to post questions as they come to mind onto the course website, and look for updated or additional bugs code for this particular example later today or tomorrow. Just as a preview, on Wednesday we'll be getting into or finishing up the traditional meta-analysis piece of the course and starting in on some of the early stages of model-based meta-analyses. So thanks for attending, and we'll talk to you all on Wednesday.